The laser, a useful tool in industry, science, and medicine.
When it comes down to it, a laser is just a light with extreme focus. It's both elegantly simple and extremely complicated. And it changed the way we literally see the dimensions of our Earth, our moon, the planets, asteroids, and beyond. But it was a long road to get there. Back in the 1980s at NASA, using lasers to measure physical features from space was too experimental, too risky. Fortunately, it was also a time of change and risk-taking at Goddard Space Flight Center.
In the 1960s, there was probably not much question that when a science or applications mission came up, for the most part, it went to Goddard. And we've got to do a better job of selling ourselves and being sure that we're responsive to what headquarters is looking for in terms of the competition between ourselves and other NASA centers.
I came here as hired by the center director, Noel Hinners, in '85, and he said, so what do you want to do? I said, I want to map the topography of Mars, at this scale, not the scale of buildings. How do we do that? And he goes, well, we got folks, they do stuff. And so I met a few of them very quickly, and that was Jim Abshire, John Degnan, Jack Buffton.
We started working with laser remote sensing instrumentation. It was the same type of instrumentation that communicated from ground to satellites in satellite laser ranging. We could do a little airborne laser remote sensing, and Garvin and I sort of found each other through that. I said, come on down to Wallops and we'll fly this. And he said, oh, topography, Earth, yes, I want to measure it.
We literally took a T-39 training aircraft that was put together by the Wallops team, really impressively, and bolted in a big telescope with a laser and went flying out in northern Arizona, where I had done some field work. So out there we have Meteor Crater, we have volcanoes, and we have the Grand Canyon, and the Painted Desert. So we figured in one place we could study all this.
And it was on the strength of that Jim Garvin became interested, and it put him in a position to, when Dave Smith found that his radar altimeter was canceled because it was $30 million instead of 10.
They kept talking to me about, look, we're really close to getting a laser altimeter working. And I've been in lasers actually for 20 odd years before that, if you know what I mean, but laser ranging from the ground to spacecraft. So I was very familiar with the lasers, and I wasn't averse to it, on the contrary. But NASA offered me the situation that said, look, we've got a certain amount of money for you. We're willing to spend $10 million on this instrument. But there has to be some sort of competition. You need to choose which instrument you would like to fly to measure the altimetry.
And there were 4 candidates. 3 of them are radar, and 1 the laser that we call MOLA. There was no one in their right mind that would bid a laser altimeter. Seriously. And I was all gung-ho. I was a young guy, no gray hair. There was a lot of reticence. There was so little trust that this could be done. NASA has made a monumental achievement in both radar and visible near-infrared imaging of the surfaces of Earth and other planets. But those are flat field views. And the missing dimension, the hidden dimension, which drives where energy goes, where the water flows, stability of landscapes, is the 3rd dimension. We take for granted the map. Sometimes you need the map to do what's beyond the map.
Making those maps with that crucial 3rd dimension is what laser altimetry, or Lidar, is best at. And over the decades, Goddard's gotten pretty good at explaining just how laser altimetry works.
This is a laser altimeter, and what it does is it sends a short pulse of light
from a moving platform that's observing a surface, an airplane, a satellite.
Gets a reflection straight back off the surface.
We record that reflection and the time very precisely.
Of the pulse from the spacecraft down to the surface and back again.
Which allows us to measure the range to the surface.
When that's done repeatedly in orbit, you can build up a map.
The fast rate of light pulses and the small footprint allow LiDAR to measure with a much finer scale than traditional radars.
They had a big review, and the leading radar guy that had flown radars to Venus, Gordon Pettengill, at the end said, well, I don't know about you folks, the laser's better.
In time, Goddard would become a leader in Lidar, in mapping our Earth and planets with unprecedented precision. But for now, they had to actually build the first one.
The requirements were, of course, we were in a much higher orbit. The orbit was faster than going around the moon, so we needed a larger telescope. We needed a more sensitive detector. We needed more laser energy. So in order to put our concept together, we had to gather a team. And then we had to convince their management that this was not a crazy idea and that we actually had a realistic chance of making this happen.
We worked a lot of hours. I can remember Jim talking about, working 10-hour days, and I was doing about the same. But, it really didn't matter because it was so exciting to be working on something that was going to actually map Mars.
I was fresh out of getting my master's degree in computer engineering. I was young. I had to really dive in deep. I had to spend about 2 years working with the team on algorithms. How are we going to find the surface of Mars? How are we going to track it? How are we going to compute all the precise ranges?
And we were sort of making our way. We were defining the rules as we went.
We finished the instrument pretty much on time, and certainly as they said in the letter to me, look, if you don't make it on time and in budget, we will fly a brick instead. Okay, we're not going to hold this mission up. I knew about planetary missions; they have to go within certain windows. But anyway, we made it all right.
5, 4, 3, 2, 1. And liftoff of the Titan III rocket with the Mars Observer and America's return to the red planet. And the vehicle has cleared the tower.
We've got X-band launch at Canberra. Yeah, all right. Roger, I have that report.
Very happy crew. And Mars Observer is on its way to Mars. Trajectory is right on the money.
We've assumed that the spacecraft properly executed its orbit insertion sequence, and we presume the spacecraft is in orbit about Mars, but we have no positive confirmation of that because, as for the last 3 days, we have no communication with the spacecraft.
To say you simply don't know what happened. It could be in orbit. It could have flown past the planet.
What are the scientists doing to relieve the tension in there?
Screaming loudly, probably.
We still don't have communication with the spacecraft. However, we are very hopeful and we're cautiously optimistic that communication
Every day,
will be
in fact,
restored.
without communications clearly lessens our probability of success.
You say, though, we give up.
We have not given up.
On 21 August 1993, a tragic event occurred. Communications with the Mars Observer spacecraft were lost during a sequence referred to as the pressurization sequence. This was a sequence in preparation for insertion to orbit about Mars.
Once again, we're always trying things because they're hard, not because they're easy. And so once in a while, we're going to have a failure because we are trying hard things.
That I had been fully anticipated that we could have problems with this instrument. This was a new ball game completely, okay. But I was not concerned about the spacecraft. It never crossed my mind that the spacecraft would let us down. And so this was a blow in the sense of, wow, something I completely didn't expect.
We held out hope for a while that maybe it would come back, maybe they'd find it or recover it or something, and then eventually that settles down and you realize the mission was lost.
I was devastated. I think we all were, and it really wasn't clear at the time whether we were going to have a follow-on to actually do what that mission was supposed to do.
So that was extremely hard to take. What made it easier is the amount of time we had for grieving was actually pretty short.
NASA decided that we want to continue this and go back to Mars. And so we had to snap out of it, literally, and get back to thinking about and fighting for the next mission, which is Mars Global Surveyor. It was a difficult time, and it was the first time I think I really felt I had to get in there and argue with my colleagues, but as the PI, it was particularly for me, that we needed to get back to Mars and we needed to get back with this instrument. Knowing that they couldn't carry all 6 or 7 instruments, only 4 would go, the laser altimeter had to be one of them, okay? The engineers had a chance to kind of just not change it, but do some things a little bit better.
That's what engineers like to do, is they fix all their first round mistakes in the second round and make new ones.
We were asked immediately, how long will it take you to rebuild another copy of MOLA? How much is it going to cost? Can you get your team back together in time? Do you have the parts? So there was immediately a flood of things we had to do.
Jim actually brought me in for the detector engineer who just left the Goddard at the time. So I was lucky to join the team working on the detectors. We were only given, I think it's 3 years to rebuild it. It's shorter than usual.
And everyone, all the management knew that means there's no wiggle room really in your schedule.
But the team was largely still there, and everyone is geared up to redo it since the first one didn't make it. So everyone really wanted to do it again and do it right.
While the Goddard team was building MOLA-2 for the Mars Global Surveyor mission, a small team seized a long-awaited opportunity to hitch a ride on the space shuttle with an experiment known as the Shuttle Laser Altimeter.
I think confidence comes from demonstration. Sometimes you have to do more, sometimes you have to do less.
Working personally to build that instrument, we built it at Goddard in our lab down the hall without any fancy paperwork or flight procedures or anything. We just built it.
I was hired then to come on board working on the Shuttle Laser Altimeter, and I was brought in specifically to work on precise positioning, precise pointing, and precise geolocation of the surface footprints.
And we tested it on the roof, shined it over to a bank building 11 kilometers away, lined it up, and it was ready for the shuttle.
There was a Hitchhiker Special that we flew with help from NASA headquarters on the Space Shuttle Endeavour.
Booster ignition and liftoff of Endeavour in pursuit of a Japanese satellite.
Throttle down as the orbiter prepares to pass through the area of maximum dynamic.
They turned it on for us, and the first time they turned it on, the shuttle's upside down with the laser pointing at Earth. We're over the middle Pacific.
First light showed all this fuzz over the surface of the Earth. We're all looking. We thought we got something wrong. We realized later we were seeing the boundary layer clouds over the ocean. When we came over land, the fuzz was the height of the trees.
All of a sudden, the laser pulses got shorter and shorter distances.
The first landfall of the Shuttle Laser Altimeter in the first orbit went right over the summit of the Mauna Kea volcano in Hawaii.
Well, we're extraordinarily delighted to report that the Shuttle Laser Altimeter experiment, it's a hitchhiker experiment on STS-72, has performed absolutely nominally. In fact, everything has worked even beyond our expectation.
And that was a genuine first light experience with MOLA technology, but on Earth.
Really had to get those data sets out there, and you had to get a couple people that really bought into it and built on it and convince others that this worked.
As the data from the Shuttle Laser Altimeter began to convince some skeptics, the Goddard team finished the MOLA instrument again.
Our MOLA team really came through. It was just really another great experience for many of us, including me. We were able to deliver to the Mars Global Surveyor project, and it got launched.
And we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the red planet.
6 solids burning.
When Mars Global Surveyor started getting closer to Mars, we were going to go into this aerobraking phase. That was an opportunity that we had to go ahead and turn on the lasers and see if we could track the surface.
Somebody being carried forward.
And Station 45 was having problems locking up to the 2K data.
What was that?
You said 1607 or 16...
Tell
MOLA has been turned off?
Copy, I'll probably kill my query and restart it as soon as that query's up.
Is that the nadir event? That must be the nadir event.
I'm hungry. I didn't really want those sandwiches.
Look at the laser coming back, Rob.
Rick says about 18.
It's going to be too fast and I got too much data.
Look, there's a little tiny terrace. This is the first profile of a crater we've ever seen on the planet.
That is.
Rob, nice laser.
Oh, there.
Right. We have Mars, finally. 12 years.
All right, let's take a look. I don't understand.
Over a decade later, the Goddard team had proof. Laser altimetry worked. It could map distant craters and valleys and mountains. It changed the game.
Today, we've ushered in a new era in the remote sensing of Mars.
And this particular data set that we've acquired has in fact enabled us to generate what we consider a very detailed description of the shape of the planet Mars.
This has significant implications for the flow of water early on Mars.
We believe this is one of the youngest features on the planet. We're seeing a planet that is very different from Earth. And it's telling us something about the Earth in an indirect way that says that not everything works in the way that we originally had in mind.
The kind of measurements that we're making now are allowing us to, characterize Mars on timescales of days to years now. And then the next step is to try to go back eons and try to figure out what changed on Mars.
I mean, at that time, we used to brag that Mars was mapped better than the Earth. The accuracy of MOLA was so good, and after a couple of years, the coverage was so good. It was definitely a more accurate map of a planet than any planet.
And this came out of it can't be done in the mid-'80s to a tool that we now accept as the standard.
For those of us that worked on MOLA, it was transformative. It wasn't at a destination or a place that we were as much as a place that we would become.
Following MOLA, in some ways we were in demand to consider whether we could provide a laser altimeter to another mission.
A few missions, actually. It was no longer a question of if LiDAR could work, but where else it could work. But as the opportunities to test the limits of LiDAR arose, so did the challenges ahead. The Goddard team quickly began to see the evolution of LiDAR missions, building on the successes of new frontiers mapped by MOLA.
We've measured the changes, the seasonal changes in the Mars ice caps, both the North Pole and the South Pole. We've measured the volumes, we've measured the mass that's involved in that. We now have a density. So now we know the kind of processes that are taking
Dave Smith invited me to be on the MOLA altimetry science team. And that was because of my experience with using altimetry over land rather than ocean processes.
Zwally was an obvious choice to study the Martian ice caps for MOLA, given his decades of expertise with our own polar regions, studying the ice sheets of Greenland and Antarctica through the 1970s and 80s.
And then as we went into the 80s, NASA was sort of the beginning of the development of the Earth observations program.
So the Earth observing system, I think, will be the first effort targeted at looking at the whole Earth system as a system, rather than just the little components that make it up.
Somewhere along then, I teamed up with Jim Abshar.
Jay had been pushing for a long time for a dedicated ice altimetry mission, which turned into ICESat-1.
Designing ICESat-1 marked a major leap in what LiDAR needed to do and how challenging it would be to do it. To measure the changing ice sheets, the LiDAR had to be far more precise, cover the same tracks season to season, and it needed more power and a larger instrument, which meant much more time to build.
We built a simulator for ICESat-1 that allowed us to sort of figure out how precise it could be, how we would process the waveform data coming back, how we would track the surface.
This algorithm was much more complicated than anything I had ever worked on before.
But all this meant essentially for the ICESat mission, you needed a much more advanced version of MOLA.
In Mars, we really didn't know what was there until we got the measurements. So we were doing discovery. On Earth, we have to make quantitative measurements about what's happening.
4, 3, 2, 1. And we have ignition and liftoff of NASA's ICESat and ChipSat spacecraft looking at stars and ice.
But after, we'd worked on glass at that point more than a decade, and it already launched, and usually you think, okay, now we're going to be able to enjoy the data coming down, and what can we see in the data? But there was much more, what is this mystery we're seeing? Why is the laser energy going down? Things were not working the way we expected them to, and there were mysteries, and we weren't expecting, after MOLA in particular, to have mysteries at that point.
One of these unexpected mysteries came down to the wire. Several wires, actually.
What happened on glass was the laser diodes had gold bond wires and indium solder. If you bring these two metals together, even though they're not reactive, they do combine to form gold indide.
The gold indide ate away at the wires, leading to added thermal stress, and eventually the failure of the first laser. And the second and third lasers were degrading as well. Tough decisions were ahead.
When these missions operate, there's a lot riding on the missions. You don't want to make any mistakes. You want to optimize things as best you can.
The question was, given that we would have so much lifetime expectancy from the lasers, well, the scientific decision was that the best way to use that was to operate for periods of about a month and do that 3 times a year.
That decision paid off when ICESat showed dramatic change in land ice around Greenland, and it also proved that Lidar could be used to measure something called sea ice freeboard, a major breakthrough in determining sea ice thickness and an essential science goal for the future of ice measuring satellites.
Even though the ICESat project required much more care and feeding, it really laid the groundwork for all the subsequent missions that Goddard has flown.
Around the same time that ICESat was developed, Goddard was tasked with designing a laser for measuring a place far from any icy poles.
Sean Solomons was the PI of Messenger, and he said, I've been asked to PI a mission to Mercury. I really want a laser altimeter on board. Can you make one that will work there? So the short answer seemed to be, yeah, I don't see why not, but there will be extreme thermal circumstances that we'd have to worry about.
That was a really tough one because you fly in close to the 800-degree planet and then you have a 12-hour orbit.
The temperature changes by tens of degrees in a few minutes.
It had to always shield itself from the sun constantly, which meant that in orbit it was often at a very high angle. It was a challenge to try to continually figure out where the surface of Mercury was.
And then they wanted it to be small, much smaller than MOLA. I think it's ended up to a quarter or a fifth of the size.
But I remember the manager who was running it for us at the time kind of said, you realize I've thinned every wire in this electronic package so thin that you better not look at it twice because it might break. But that's the level we had to go to get within the 7 kilograms, okay? And MLA was the laser altimeter that we proposed, and this was really pushed the limits of what we could reasonably expect to do.
Despite the extreme environmental gauntlet, the Mercury laser altimeter kept on collecting data for 4 years, right up until the very end when Messenger crashed into Mercury in 2015. But before that, it captured historic views of the planet's topography.
It is time for America to take the next steps. Beginning no later than 2008, we will send a series of robotic missions to the lunar surface to research and prepare for future human exploration.
And then one day, a president, I think it was George Bush, suddenly decided we're going to go back to the moon. Wow, all of a sudden, okay?
We've been thinking about putting a LiDAR around the moon for a long time, actually.
And I really wanted to have a crack at doing a good one instrument for the moon. I mean, my interest was in gravity and topography, two things that need to come together to measure the structure of a planet.
And then all of a sudden, we got a call from headquarters. Can you design a LiDAR around the moon to map the moon, to map the topography?
And so the instruments were chosen from proposals based on the ability to help select sites and determine the safety of landing in particular sites on the moon.
The LiDAR would be the Lunar Orbiter Laser Altimeter, or LOLA, and it marked another leap into laser altimetry.
We also came up with the idea of having multiple beams.
We managed to put 5 beams on the surface, and that kind of changed the observational strategy, if you know what I mean, of 5 parallel beams.
But after launch, Lola was suspiciously silent.
When Lola started, I think that was just devastating.
We didn't get any measurement at nighttime when we first turned on. It was quite a shock, and it was the first LiDAR that didn't work at the initial turn on.
The people that are heavily involved in the instrument development, you're pulled back in if there's surprises that occur.
On Lola, the blankets were all tied tightly to the beam expander and the telescope, and this germanium black kapton, which we didn't test with, was very strong.
And then we caused a misalignment.
I remember we discussed whether we wanted to check the alignment at spacecraft level, and we just decided not to do it. I think that was my fault, because we could have. We started in the worst possible orbit for that failure mechanism. And so we were out of alignment, and we had no signal at all, and that was just it was a tough couple of weeks.
Yeah, it is a lessons learned for life for me.
A couple of weeks later, we noticed a little blip at the South Pole, and so we had some hope. And it eventually just, as the orbit progressed, the signal kept getting stronger and stronger on the daylight side.
Despite a bumpy start, in time, Lola and the Lunar Reconnaissance Orbiter mission became revolutionary in mapping our moon.
And it's turned out to be exceptional in terms of describing the topography of the moon. As a result of Lola, I think largely, if not the others as well, the doubts about whether a laser altimeter, for example, could last, age limits, lifetime limits on the laser altimeter were dispelled.
The shape of what we build, live, work, study, operate on, whether it be on the Earth, the Moon, Mars, wherever we're going, matters. Knowing that at a scale where we can understand what's going to happen, what has happened, and predict what could happen is really important. Laser altimetry, as developed here at Goddard, went from an idea to try to capture that into something we can actually do.
In 2018, NASA launched 2 next-gen LiDAR missions specifically to look closely at our changing planet. But if over 3 decades of LiDAR missions taught us anything, it's that laser altimetry at Goddard is an evolution of technology, propelled by scientific curiosity in the face of almost certain setbacks. Take the story of the tree-measuring LiDAR, the Global Ecosystem Dynamics Investigation, or GEDI.
GEDI had its genesis really in all the innovative work that had been done with LiDAR at Goddard. Some of those innovators, this was Jack Buffton and Brian Blair at Goddard. Brian had an instrument called Slicer that was flying around taking these cool LiDAR transects. And then they put an instrument up in space, the Shuttle Laser Altimeter, and I saw some of that data. I thought, wow, this is really cool. We've never been able to look at canopies in 3 dimensions like this. There's certainly got to be some applications to this.
The Shuttle Laser Altimeter was the first real test for LiDAR and provided the momentum for MOLA to take on Mars. But it also gave us a glimpse at what LiDAR could measure on our own planet. And so the push for the Vegetation Canopy LiDAR, or VCL, began.
It was a really innovative mission. We were trying to do something that hadn't been done before. But we were optimizing it for vegetation. Vegetation is very different than if you're looking at ice, or if you're looking at Mars, or if you're looking at the moon, because you have to have enough laser power to get through the canopy and get a strong return underneath the ground.
The VCL team could build lasers strong enough, but they couldn't get them to last very long. And that proved too risky for a very cautious NASA in the 90s.
After that happened, we focused on the airborne LIDAR program. And this is again with Brian Blair using a really innovative instrument he had called Elvis, the land vegetation and ice sensors, I believe it's called.
If you really want to get down to really high resolution and looking at the sort of landscape scale changes over the Earth, you need a swath mapping system. So sort of in the mid-90s, we started working on Elvis, and we really worked on that in large part because people said it couldn't be done, and it's really kind of drove us to see how much we could get out of that system.
Airborne missions were successful at keeping that momentum going, especially in the long periods between satellite launches.
Sort of a core of us kept going year after year, going from one instrument opportunity to another, and sort of making opportunities if we didn't have any. The thread that kept us all going was the airborne system.
Airborne LIDAR really plays a role at helping us understand how things work in real world settings.
Yeah, that's definitely the best way to go, is to build the hardware, get some data over real terrain, and actually show that it meets the requirements, that you can scale it to space.
But along the way also, as we were flying, as we were collecting those data sets, we were releasing those publicly and letting people experiment with them and get comfortable with them.
Dubaya, Blair, and others leveraged the success of Elvis to propose a new satellite mission, Destiny, a combined radar and LIDAR mission that could see through clouds down to tree canopies. However, NASA budget cuts sidelined a couple of Earth science missions, and Destiny was grounded indefinitely.
And that was a devastating blow because we'd now been trying from 1995 and now it's 2010. We've been trying to get a LIDAR that was meant just for vegetation structure into space, using the best people in the world who are at NASA Goddard to do this. And at that point, I've been doing this 15 years, maybe I'll just quit. But of course, we really didn't quit. So we said, well, let's look for another opportunity.
That opportunity was on board the International Space Station with the GEDI instrument. GEDI wasn't just another successful LIDAR. It was the end of a very long road, hard fought by scientists and engineers dedicated to pushing the limits of what LIDAR could do.
We've been really pretty happy about the success of GEDI thus far. GEDI, again, is the first LIDAR that's been in space that was optimized to measure vegetation structure. And it's created an enormous amount of data. We've conservatively done about 10 billion estimates about getting those tree heights and getting that canopy structure.
But ultimately, we really wanted to get at the carbon content. What role do forests play in the carbon cycle?
GEDI has been steadily gathering data, chipping away at the global question of just how much carbon dioxide trees take out of the atmosphere, a big piece of the climate puzzle. The current LIDAR missions are all about building on the past.
Things that we, in fact, have only just begun to think about from pictures. Now we have the third dimension.
ICESat will add the third dimension.
ICESat-2 adds the third dimension, the elevation.
Pushing the technology to get at deeper science questions. And so came the next generation of ice-focused laser altimeters, aptly named ICESat-2. Its single instrument, Atlas, was designed to precisely measure small changes in the shrinking icy poles of Earth. To get down to that level of accuracy from space, everything had to be much better.
It's this story of these incremental improvements through time, and with each mission you're leveraging the lessons of the last mission. It wasn't a short process for ICESat-2, even though we knew a lot and had learned a lot over the last 20 or 30 years. Each mission, has its own challenges. All of the easy missions are done, as they say.
The first iteration of the instrument was going to be very similar to glass. As it turned out, the group that wanted the more complicated instrument won. So then they came back and said, okay, instead of digitizing a 40 hertz or 50 hertz laser or whatever, we're going to fire this beam to the ground and then individually time tag each photon that comes back.
There were so many requirements, there were so many constraints. We had constraints on the software capability, we had constraints on the storage space, we had constraints on the memory.
By photon tagging, I mean, they had built the detector system and the detector electronics. They were just, it was like a fire hose of data coming into us.
Atlas has 6 beams, and it records elevations for each of those 6 beams 10,000 times a second, as long as there is reasonably clear skies that the laser light can go from the spacecraft to the ground and back again.
The Earth is much more complicated to work with because of the clouds. The algorithm could easily be confused and start following, the cloud surface. I was the lead for the receiver algorithms team. The responsibility of making this work fell on my shoulders. I had sleepless nights, I have to tell you, thinking that I wasn't going to be able to make this work.
In order to maximize the return from these data, a key component was determining the location on Earth of the laser bounce point, a process called geolocation.
So what we do in geolocation, we get the position of the satellite really accurately, we get the pointing of the laser beam very accurately, and then we have the range from the altimeter, and we add all those together to give us where that bounce point came from. Without the geolocation, you have lots and lots of error, and you wouldn't be able to measure the change in the height of the ice sheets.
We overcame what I think was fairly insurmountable problems, but everybody took their own piece of the puzzle and everybody worked it.
ICESat-2 launched in 2018, and months later began gathering data that shed new light on how fast the ice sheets are changing, how thick the sea ice cover was in the Arctic, and even measured beneath the surface of the water, up to 30 meters, a kind of bonus science result for a team that worked tirelessly to push the limits of the Atlas instrument.
Goddard has really played a lead role in the world in moving LIDAR from airborne and ground-based missions into space.
I mean, the future is in the hands of the creative people here and elsewhere in industry that can just take this and run with it. We've revolutionized how we look at our own world, and the future is wide open. Winds, aerosols, trace gases.
I've been spending a lot of time and most of the past decade working on a LIDAR to measure atmospheric CO2, and we've been flying that fairly regularly on aircraft. We've got this remarkable data set that really proves, I think, our approach really works well. There's many other gases that are very important, particularly with global warming, that lasers can help us monitor.
Over all these years, we've developed these different techniques and lasers and detectors and put all those together into a recent system that we've just started working on, the hazard detection LIDAR. Essentially a really precise, really fast LIDAR that helps land safely on a planet. You want to make millions of measurements in a second. You have to process and produce those data in real time.
This technique is giving us better understanding of where we live, where we want to live, where we want to explore in ways that are fundamental. So I look at it as it's a measurement engineering success story, and masterpieces of engineering often lead to masterpieces of science.
With MOLA 2 being on MGS being the ones I look back on most, as being absolutely, they really shook me up as well, and I think they shook up the community as well into what you could do with a laser altimeter.
And I'm amazed at how much knowledge can be gleaned from this relatively simple measurement, just measuring time of flight.
So you cannot just build just one LiDAR. You need a sustained team who's been building LiDAR for some time, so you can pass on the lessons learned and so forth.
To see that rocket go up with the thing that we had worked on for so long finally become a reality. I had my family with me, many of the other scientists had their family. The reason many of us also bring our family there is because of the sacrifices our families had to make this a reality. Because of the long nights and being away and the amount of effort we had to put in.
There's a lot of special pieces that need to go into it, and a lot of experience that's just built through decades of doing. Across Goddard, they bring in new people to learn through mentorship and learn by doing on these projects.
What I love about NASA, and in particular Goddard, is still this way, but it was really a meritocracy, meaning it didn't matter what school you went to, what degree you had at some level, right? That just got you in the door, but how you progressed through NASA was really based on what you did.
I never suffered from being, I never was not promoted, or I never was told I was doing a bad job or anything like that because I was a woman. Well, I think Goddard has been a fantastic place to work.
When you get to work on something new and exciting, that is privileged. It's a privilege.
Getting good people to work with you, knowing what risks to take, those are key factors in success of all these things.
It's working with the scientists. You're in the same team, you're in the same room, you're in the same meetings, you're down the hall from each other, you're in the same organizations.
Our successes of the past are due to some very simple things. And that is that Goddard is, as a center, a people with an incredible dedication and devotion to their work.